Hello everyone, and welcome back to The Explainer. Today, we are going to take some pretty complex ideas and, well, make them perfectly clear. We're diving into something truly fascinating, the hidden geometric measurements of physics. You know, when we think about measuring the world around us, we almost always default to distance, weight, or just the ticking of a clock. But how exactly do we measure the angles and the actual curves of physical space itself? Well, that is exactly what we're going to unpack today.
So think about this for a second. Are there units in physics that actually don't measure length, mass, or time, but still play an absolutely massive role in science? It's a really great question. In the standard SI system, we're all incredibly used to the classics, right? We measure length in meters, mass in kilograms, time in seconds. Those are our fundamental base units. And then, of course, we have derived units, which combine those basics to measure things like velocity or force. But beyond our standard meters, kilograms, and seconds, there's a bit of a mystery regarding how we measure the angles of space.
And historically, that mystery was solved by a very specific concept. For the longest time in physics, there was a completely separate, special category known as supplementary units, and these were used exclusively to measure angles. They weren't base units, and they really weren't your typical derived units either. They kind of just existed in a VIP club all their own, serving a highly visual purpose in math and physics.
Now, there were only ever two units that belonged to this exclusive club, so allow me to introduce the absolute stars of our explainer. The dynamic duo of the radian, which is abbreviated as rad, and the steradian, abbreviated as SR. These two units are literally the keys to unlocking both two-dimensional and three-dimensional geometry and physics.
All right, let's start with the basics. Part 1. Meet the radian. To really grasp this, we need to focus entirely on flat, two-dimensional planes. Nothing popping out at us yet, just flat space.
What's really cool here is how beautifully simple the actual definition is. 1 radian is defined as the angle made when the arc length is exactly equal to the radius of a circle. Let's visualize this. Imagine the center of a circle. Draw a straight line to the edge. That's your radius. Now imagine taking that exact same length and just bending it along the outer curved edge of the circle. The angle that gets created at the center by that specific curved distance, boom, that is exactly 1 radian.
Mathematically, it is wonderfully elegant. The angle simply equals the arc length divided by the radius. See? Incredibly non-intimidating. You're just taking the distance traveled along the curve of the circle and dividing it by the distance from the center. When those two numbers match perfectly, your result is 1 radian.
To brilliantly illustrate this in the real world, imagine a cute, colorful 3D bicycle wheel spinning along the ground. As this adorable wheel rotates, it covers a specific distance along its outer circular rim, right? Well, if you were to measure the distance the wheel rolled along the ground, and that distance perfectly equaled the length of the wheel's spokes, its radius, then that wheel has rotated exactly 1 radian. It just makes the abstract math suddenly feel very tangible and easy to picture.
So if we take that cute bicycle wheel and roll it all the way around for 1 complete full circle, how many radians are we talking about? The magic number is 2 pi. Since pi is roughly 3.14, a full circle contains exactly 2 pi radians, which calculates out to roughly 6.28. That means it takes just over 6 of those radius length arcs to wrap entirely around the perimeter of literally any circle in the universe. Now, you might be wondering, why does this actually matter for us? Well, radians are the absolute gold standard in physics for anything that spins, turns, or oscillates. We use the radian to calculate circular motion, angular velocity, which is just a fancy way of saying how fast something is spinning, and even wave motion. Because it directly links the radius to the distance traveled, it makes complex physics equations incredibly clean and super easy to work with.
Okay, part 2. Meet the steroradian. We are completely leaving the flat, 2D paper behind now. We are stepping out into fully three-dimensional spherical space.
Where the radian measures the flat angle, the steradian measures what we call a solid angle. So let's define it. 1 steradian is the solid angle formed when the surface area on a sphere equals the square of the radius. I want you to picture a 3D sphere, like a globe. Instead of drawing a single line along the edge like we did with our flat circle, we're now drawing a patch, a literal 3D area on the surface of that sphere. If the area of that patch is exactly equal to the sphere's radius multiplied by itself, the radius squared, the 3D cone-shaped angle that shoots out from the center of the sphere to fill that patch, that is 1 steradian.
A formula perfectly mirrors our 2D version, just leveled up for 3D space. Solid angle equals surface area divided by the radius squared.
Because we're now dealing with an area on the surface of a sphere rather than just a simple curved line, we have to square the radius in our formula. It's a beautifully logical progression from the flat radian right into a deeper dimension.
To bring this one to life, picture an adorable, glowing 3D light bulb. When you turn it on, the light doesn't just travel in a flat 2D strickle, right? No way! It expands outwards in every possible direction, creating a literal sphere of illumination in 3D space. When physicists need to measure how that light spreads out as it moves away from the bulb, they measure that three-dimensional cone of spreading light in steradians.
So the absolutely crucial point is this. If a flat circle is 2 pi radians, what's the total solid angle of a complete fully enclosed sphere? The answer is exactly 4 pi steradians. And it doesn't matter if you're looking at a tiny glass marble or the entire observable universe, the full 3D space around a central point is always exactly 4 pi steradians.
Because it measures how things spread outward in 3 dimensions, the steradian is incredibly vital in real-world science. It's primarily used in measuring light intensity, analyzing how radiation disperses from a source, and it's heavily utilized in astronomy to measure the vast 3-dimensional fields of the cosmos.
Now that we completely understand our dynamic duo, I have to let you in on a little secret. There's actually a modern twist to this whole story. Science is always evolving, and the way the scientific community categorizes these two geometric measurements has recently undergone a pretty major structural change.
The twist is this. Today, supplementary units are no longer a separate category. That's right, that exclusive, special, historical club in the SI system that we talked about at the very beginning of the explainer, it officially no longer exists. The powers that be in the scientific community decided that having a third, completely separate category of units was just unnecessary.
Instead, radians and steradians are now officially classified as dimensionless derived units in the modern SI system. Now, why dimensionless? Well, if you remember our formulas, we were dividing a length by a length for the radian and an area by an area for the steradian. The physical units, like meters, actually completely cancel each other out. So they're derived from base units, but they don't carry dimensions like length or mass themselves. They are just pure, elegant ratios of geometry.
Let's lock this all in with a quick rapid-fire summary. We have the radian, our absolute master of the 2D plane, measuring the flat angles of circles, completely essential for calculating spin and rotation. And then we have the steradian, our master of 3D space, measuring the solid, cone-like angles of spheres, completely essential for tracking how things like light and radiation expand outward into the universe. Just two perfectly paired tools to measure the geometry of reality itself.
And that brings us to the end of our journey through these amazing geometric units. If decoding these hidden measurements made physics a little more enjoyable for you today, please remember to like, share, and subscribe so we can keep bringing you clear, focused explainers just like this one. But before you go, I want to leave you with this thought. If we can demystify the very angles of 3D space, what hidden physics mystery should we decode next? Drop your most challenging topics in the comments below, and let's keep exploring together.